Welcome back, everyone, to another week of Physio Psych. This week, we're going to be talking about cellular physiology. This is the inner workings of the cell, and we're building upon last week where we talked about all the different components that support a neuron and support what it does, including glial cells, but also all of the organelles inside of the neuron. And this week, we're going to start talking about function. Now, one thing that I want to make abundantly clear is that just because the lecture today is going to be short does not mean that it's not important. In fact, it's just the opposite. It is one of the most important lectures for the entire semester. So this is one where you should nail down the details. This first quiz and this first series of information is so important to everything else that we do, and this is why we spend so much time breaking it down piece by piece by piece. Okay. We're going to talk about how neurons come together in a circuit. So this is getting back to this idea of inputs and processing and output that happen. And this is incredibly important for what you need to do. So we already talked a little bit about this in last week's lecture. We have neurons that are doing sensing. We have some sort of processing. We have some sort of an output. And at the simplest level, when we have communication between neurons, we can have one of two things happen. We can either have facilitation of a response or we can have inhibition of a response. In a very simple example, we might have a sensory neuron that detects something that happened. In the case of the example here, some sort of a painful stimulus. You touch your hand on an iron or a hot stove, ouch! Doesn't feel good. But before you can even process how bad that feels, your central nervous system is already diving in because the sensory neuron that receives that hot stimulus generates an action potential, right? This is the primary signaling mechanism of a neuron. It's an electrical signal that travels from the end of the sensory neuron, and it goes all the way, in this case, into your spinal cord. And then what happens is we have some bit of processing that happens. And in this case, we have an interneuron in the spinal cord that receives the signal. And because it's receiving the signal from another neuron, it too generates an action potential. And so we feed this forward. And it feeds forward to a motor neuron, which then sends a signal out to the muscle to telling it to contract and to pull your hand away. And we have these sort of reactions all the time. And in the most simple form that we can possibly get, this is neural communication. It's the passing of messages from place to place to place. So again, motor neuron fires a contraction, we get a withdrawal behavior, and in the simplest circuit possible, we have now gone from an input to some very simple level of processing to an output. We have behavior. And in fact, all of this in this example here doesn't even involve your brain. It doesn't need it whatsoever. So what happens when the brain does get involved? Well, we have some cases where we don't want to make a response, where we want to inhibit a response. What would happen in those cases? We have to do something to this entire series of events that we're talking about. We have a painful stimulus, we have an interneuron that activates this motor neuron, and then we have a withdrawal reflex. But what happens when we don't want this to happen? So this is the case where we talk about that guy. You all know that guy. The guy, he's the, hey guys, watch this guy. Hey guys, I can set my arm on fire, it won't hurt much. Hey guys, I can take this steaming bowl of soup out of the microwave and carry it across the room because I'm tough. That guy. We're going to talk about that guy. So what's that guy doing? Well, that guy still has all of the same signals coming in when he decides he's going to take that ridiculously hot bowl of soup and carry it across the room and be super tough while doing it. So there's still a sensory neuron and it's still receiving a signal that this is really hot. And there's still all of these interneurons that are passing a signal forward to a motor neuron. So somewhere along the way, we have to do something to stop that message. And this is where the brain can get involved. This is where we become interesting kind of human beings with free will, because you might have then a neuron in the brain that says, no, it's okay. Don't make that flinch response. I don't need to. I don't want to. And in this case, we have an axon coming all the way down from the brain to the spinal cord. And what it does is it puts a block on the motor neuron. One axon from the brain coming in, and in this case, it can send an inhibitory signal. Instead of one that activates an action potential, its job is to come in and shut down the action potential. And in this case, the motor neuron no longer fires, and so we have this entire series of events. And of course, they're very well designed if you think about it, because it's good to know that something is hot, and it's good to know how hot. Maybe even there is a point where something is too hot and you need to let something go. We've all done this. We think, I'm going to pick up this hot bowl from the microwave, and then as you get halfway across the room, you say, okay, too hot, too hot, too hot. I need to put it down. But on the way through that, you've pretty much told your brain to prepare for the fact that something is going to be hot. You've told it to not throw your soup across the room because we all need our ramen noodle soup. And then you've been able to make a response, at least for a period of time, that drives your body to do something that it might not normally want to do if it were just reacting on reflex alone, if it were only your spinal cord acting alone, and instead we drive this inhibition. So an important thing to realize here is that this withdrawal reflex, at least in terms of the spinal cord, is still generated, but the final behavior is eliminated. And this is a lot of times what happens when the brain gets involved. The other important thing to recognize here is that this is a very simple illustration of the two types of signaling that we can have in the nervous system. We can have excitatory signaling, where an action potential goes from place to place to place, and we just pass the message forward. But we also have chemical signals that act as inhibitory signals, and these inhibitory signals act to counteract some of the processing. And for the most part, this is what we can boil down the signaling that happens in the brain and in the central nervous system and in the body down to. So to take a look back, just because I think it's important, again, I told you all, I think of things as a systems neuroscientist, and I like for all of you to try and do that too. So in thinking back through our input, processing, and output, in this case, we still have a painful stimulus, but the processing in this case ends up, there's still the passing on to the interneuron and all these things, but in this case, the final result of the processing is that the brain inhibits the motor neuron, and then the output changes to no response. And in a way, it's a purposeful non-response. So then the next thing we have to understand is how all of this comes together. And the fundamental principle that we need to talk about in order to understand this is what is an action potential and what is neurotransmitter release. We talked a little bit about the different pieces of the cell, and one of the pieces that we mentioned in last lecture is the cell membrane. But the thing that I might not have emphasized enough there, might have said it, but I probably didn't emphasize enough, is that the cell membrane is the single most important piece of a neuron. It's what makes a neuron a neuron. And this is because the cell membrane of neural cells is incredibly different from any other cell that you might come across. And this cell creates this electrical and chemical buffer. Remember, it's made up of a lipid bilayer, or two sets of lipids formed together, which means that it is incredibly hydrophobic. And it does that in two directions. It keeps what's in the cell in and keeps what's outside of the cell out. And what this does then is, by creating this electrical and chemical buffer, it gives the neuron the potential to be dynamic, to drive change whenever it gets a signal. And I referenced before, it's almost as if you have two different sides of a battery and they're just waiting to be connected. You have a ton of potential energy sitting here. And this brings us to the idea of two incredibly important forces. Now, if you've had chemistry, you've probably learned a little bit about these forces. The first one of them is called diffusion. So what this means is that molecules will naturally flow from a high concentration to a low concentration. And if any of you are sitting bored at home in a pandemic, which I would guess that maybe just a few of you are, then you can do a little experiment. You can go in, grab a glass from your kitchen, grab some sugar or some salt, and you can put a ton of it at the bottom. You can just pour some water on top. And don't stir it, just put some water on top. And then watch it for a day, 2 days, 3 days. And what you're going to see is that without your action, that pile of sugar is going to start to disappear. And I can't tell you how long it'll take to disappear because that depends on how much sugar you decide that you're going to put in. But you will see it start to disappear because you're going to have those molecules going from the high concentration in the group of sugar out to a low concentration. And this has everything to do with just how densely grouped certain molecules are. Okay? So in the case of the neuron, we have many different proteins and molecules that are either at a higher concentration inside of the cell or outside of the cell. And the reason that diffusion is important is that means that these molecules want to move from the outside to the inside of the cell, or the inside to the outside of the cell. Now, the important thing here to think about, I think the important identifier is that what matters is what the molecule is. So in the example of the experiment that many of you are probably going to go do, it matters that the identifier is sugar. This is in contrast to electrostatic pressure. Now, at first, most people tend to think of these as being incredibly similar, and what I would challenge all of you to do is to take some time to understand exactly why they are different. So in this case, alike ions. And when we say alike ions, what we mean are ions with either a positive charge or ions with a negative charge are going to want to repel each other. So this you've probably all done in the past. If you've ever played with multiple magnets at the same time, you know that there's one side of a magnet that's going to stick to another, and then there's another one that's going to repel. And this has everything to do with charge. If you put two positive ends of a magnet together, they're going to repel. And if you put a positive and a negative together, they're going to attract. So in the case of neurons, these positive ions we call cations, they are going to repel other positive ions. And the negative ions that we call anions are going to repel other negative ions in that exact same way as a magnet. And what matters here is not the identity of the molecule, but the charge of the molecule. So if we have things that have the same charge, like sodium, which has a positive charge, and potassium, which has a positive charge, those two, even though they're different, right? You could think sugar and salt if you want to, using our analogy from before. Those two want to repel each other simply because they have the same charge. And if we have two things with opposite charge, again, we could use sugar and salt as an example. I don't know the exact charge of sugar off the top of my head, but the idea is if they have an opposite charge, they're going to want to attract. They're going to want to come closer to one another. So why does this matter? Well, again, we have certain ions at a higher concentration outside the cell than inside the cell. And so if they're all grouped and bunched together and they're all positive, they're going to want to push away from each other. And they're going to want to spread out as much as possible. You could try and corral a bunch of magnets from your refrigerator into a very small space on your dining room table later, and you would see this. There's going to be a certain place where all of the magnets will comfortably separate from one another. And the way that this can happen inside the brain is that we can, again, go from kind of the high location of charge to lower locations of charge. In that case, that means going from outside of the cell to inside, or inside to outside. Why do we care about explaining these two separate forces in such detail? Well, the important thing about explaining them in detail is that these two are independent forces. So I can have a high concentration of something, and that would mean that the molecules want to separate because of the concentration. However, they might be pulled to stay closer together because of electrostatic pressure, because maybe they're already sitting in a zone that has a lot of opposite ions, even though they're at a high molecular concentration. So the fact that these two can work independently of each other is kind of key for the different things that drive molecules in and out of a neuron and at specific times. So if you think about this then, let's take the example here. We looked at before, we were talking about a cell membrane. We said the cell membrane is important for creating a barrier. And in fact, if you look at the example I have here, we show that sodium has an extracellular concentration of 145 millimolar and an intracellular concentration of 15 millimolar. So I want you to think for a second. I'm going to give you a second to pause and think about this. Sodium, as we show here, is positively charged. And that means that we have quite a bit more positive charges outside of the cell than inside of the cell. So what should happen with electrostatic force? What should these sodium ions want to do? Okay, keep your answer to that in your head. Now, there's also a greater concentration of sodium ions. We have all of these sodium ions out here. In fact, about a 10 times greater concentration of this particular molecule outside of the cell than there is inside. So what should diffusion push sodium to want to do? So in both cases, the answer, at least for sodium, is the same. Should want to push these inside of the cell. And in fact, if the cell membrane didn't exist, that's exactly what would happen. They would spread out as evenly as possible within the brain. But instead, they're sitting and waiting. They're holding this charge, this amount of energy. It's this difference between the inside and the outside of the cell. So here's a table. I'm not going to go over exhaustively, but it shows you some of these different ion concentrations inside and outside of the cell. Sodium, as we just said, is higher outside the cell than inside. Potassium is higher inside than outside, even though it has a positive charge. Chloride, higher on the outside than inside. Calcium, higher on the outside than on the inside. And anions, which are all these different proteins and things that make up the organelles of the cell, are higher inside the cell, and they tend to have a negative charge. So if we put together all of these different ideas where we have ions concentrated in one place and not another, and that we also have these forces that become very important to how different molecules or different ions move, then we come to one of the most important concepts for what this cell membrane is able to do, and that is that it creates a membrane potential or a membrane potential difference. So what happens is that because we have higher concentrations of some of these molecules and ions, either inside or outside of the cell, then this creates an electrical charge or a difference in electrical charge between the inside and the outside of the cell. And we call this difference that's sitting here waiting all the time a membrane potential or a membrane potential difference. Either one is fine. In the case of a neuron, we have to choose the way that we measure this because, as you know, numbers are relative. I might be taller than my son, but my son is shorter than me. It depends on the perspective that we take. So if we measure the inside of the cell compared to the outside, what we see is that the intracellular space is more negatively charged compared to the outside of the cell. And in the case of most neurons, this is going to be around 50 to 70 units more negative. And in this case, the units we're talking about are millivolts. And we call this difference the resting membrane potential. And what we mean by that is that this is the membrane potential or the membrane potential difference that happens when the neuron isn't doing anything. So as you're going to study for this, many of you are probably going to head on to the interwebs so that you can look at Wikipedia or a whole bunch of other resources. And you're going to have somebody say, well, the resting membrane potential is 55 millivolts. No, it's 60 millivolts. No, it's 65 millivolts. And the answer I'm going to give you is that they're all wrong and they're all right at the same time. That's just because different neurons, depending on how big or small they are, and all kinds of other factors, might have a slightly different membrane potential. So the resting membrane potential usually varies between -70 and -50, but it can be higher or lower, and sometimes different conditions in the brain will change that. So then what changes from the resting membrane potential? Well, we talked about in the very first example at the beginning of the lecture that neurons can either be excited or inhibited. And this happens actually when ion channels or specific protein channels that we talked about are triggered to open. And we can also do this if we cause a difference in the membrane potential. And this can go in two directions. Of course, we can make a neuron inhibited, or we can make a neuron excited. So our ion channels that we talk about tend to be very selective. So the reason why this is important is because this goes along with the idea of excitation or inhibition. This is actually how this is accomplished. If you only let sodium through and that goes inside the cell, it's a positive ion and it's going to make the inside of the cell more positive compared to what it used to be. And if you allow chloride to move inside the cell, that's a negatively charged ion, so it's going to make it more negative. And those two are quite common in the way that the neurons will end up signaling. So if we have an ion channel like chloride that opens, then it will cause that internal space to become more negative, and we call this hyperpolarization. Okay. So why do we call it this? Well, the cell is already polarized. It already has a charge, just like you would think of as the poles of a magnet or the poles of the Earth. And so if we make the difference between the inside and the outside greater, we increase the amount of polarization that's there. Right? You can think of this in the way that people are polarized to an opinion or something like that. So hyper being more, polarized meaning this difference becomes more. And then of course the opposite can happen. So if we were to open a sodium channel, then we can cause the cell to become depolarized, or we can reduce the amount of polarization or this difference between the inside and the outside of the cell. So the way that all of these things come together is at the action potential. This, again, is the main signaling event of the neuron. And what we need to happen for an action potential to occur is that we need the proper kind of processing to happen. So if we have inputs coming in at a dendrite, then these might come in, and they're going to have some sort of a different magnitude to them. So any input to the dendrite that opens up an ion channel, which is what most neurotransmitter signals will do, is open some kind of an ion channel, can cause the cell to do one of two things that we just talked about. It can either become hyperpolarized from this negative voltage, this negative resting potential down further, or the cell can become depolarized. But the important thing is that each neuron has kind of a trigger point. We call this the threshold of excitation, where depolarizations need to be sufficient enough. And this is really where the cell body of the neuron starts to make a decision, because at this threshold of excitation, then all of a sudden we end up with a huge cascade. Anything that fails to meet this, we have nothing. But we end up with this huge depolarization that can happen when an action potential is triggered. And then this is followed by what we call a repolarization, and after hyperpolarization, and then back to resting. And this is the entire process of the action potential. So I know what you're thinking right now is that, okay, but how do we put all this stuff together? And that's what we need to do. We need to break this down a little bit piece by piece. So let's go back through some of these things just one more time. Remember, we're mastering these things. We have this cell membrane that acts as this chemical and electrical buffer between the intracellular and extracellular space. And this means that it keeps ions from moving, and yet we have all of these different ions that have different forces working on them at all times. And this figure from your book is a particularly good one for showing that, because it shows you not only what the different ions are, but how different forces are working on them. For example, something like sodium that has a high concentration, as we saw in kind of the moving diagram a few slides back, outside of the cell, and is also positively charged, much like the outside of the cell is more positive than the inside of the cell. That means that diffusion is going to take these many sodium ions, or these many sodium molecules, and push them inside of the cell. And because they're all positive, electrostatic pressure also wants to push them inside the cell. But this isn't the case for everything. For example, because the inside of the cell is more negative, then potassium is going to have electrostatic pressure keeping it in. The inside of the cell wants to hold on to as many positively charged ions as it can. It's very, very negative, and so it wants to hold on to them. However, there are more potassium molecules inside the cell than there are outside. There's a lower concentration out here, which means that diffusion wants to push these out. So the sum of all of these causes the inside of the cell to have this negative resting membrane potential that we see in the action potential. And it takes the sum of these two forces to push ions from place to place. So depending on what happens at any given point in time, depending on what ion channel is open, we're going to have different forces working on the cell. And what the goal is, like it would be in any chemical equation, is for these to come to some kind of an equilibrium. And again, so if we didn't have a cell membrane, we would have sodium spread out evenly throughout the intracellular and extracellular space. We would have chloride spread out evenly. We would have potassium spread out evenly. So at all times, we have these forces pushing to try to get to equilibrium. So then what we know, what starts to trigger these differences? What triggers something to happen? Well, we have chemical signals coming from another cell. We already said that axon terminals, or terminal buttons, release a chemical called neurotransmitter. And these chemicals open up protein channels that allow ions to move past the cell membrane. And when that happens, we start to see changes in where ions go from place to place. If we have a negative ion come in, then the cell becomes more hyperpolarized, moving away from this resting membrane potential even further, and moving away from zero even further, I guess I should say. And if we have a positively charged ion enter, then we have depolarizations. And as we just said, those depolarizations are the key to hitting this threshold of excitation. So if we do get to this point of sufficient depolarization, we cross this threshold and we trigger an action potential. So now is as good a time as any to talk about then the sodium-potassium pump, because you're all smart people, I know that. And what you're probably realizing is that there's no such thing as a perfect system in this world. So we have sodium, which has got these huge differences in concentration, and as it turns out, neurons are a little bit leaky. So neurons are not able to maintain all of these differences between the inside and the outside of the cell passively, and instead they actually use energy to do this. The cell membrane helps with this by keeping sodium out, and we also keep potassium in, but some leaks out over time. And so in order to create this difference, you have to start thinking about the neurons as having kind of a built-in hydraulic pump, or maybe you could think of it as a built-in battery charger, where we have this exchange channel called a sodium-potassium pump. And what it does is pretty much what any of your younger brothers or sisters or cousins or siblings do when you try and make a trade with them. Right? I know this all the time because I try and make trades with a 5-year-old every day of my life. And what always turns out when you try and trade with a 5-year-old is that you get an unfair trade. So, okay, here, I'm going to give you 2 chocolate munchkins. Okay, Dad, I'll give you 1 back. And that's exactly what neurons do, an entirely unfair trade. where the sodium-potassium pump uses ATP in order to drive the pump action. And what happens is that the pump takes 2 potassium ions in and kicks 3 sodium ions out whenever it basically uses up 1 unit of energy. So you can think 1 unit of ATP is the ticket to ride, and then we have 3 sodium kicked out and 2 potassium kicked inside of the cell. And as you see, this is an unfair exchange of positive ions, which means we now have pushed 3 positive outside of the cell, but only 2 positive came in. And that means a net negative 1 charge every time, over and over and over again. So the cells use ATP to enact this unfair trade and allows us to help maintain this resting membrane potential, or this membrane potential difference, where the inside of the cell is more negative than the outside of the cell. So those are kind of all the key pieces that you need to know for us to really put this all together. We have these forces of diffusion and electrostatic pressure, and we know that cells get a signal. So what happens at the point of this action potential? What's driving this giant peak to happen here and for the cell to come all the way back? Well, it turns out there's a lot of things happening. So ion channels are protein pores, and as we've said a couple of times today, they allow ions to enter the cell. And what's important is that they allow certain ions to enter. All of these ion channels have some sort of a trigger in order to open them, and for the most part they remain closed. And the most common thing that's going to happen, or at least the simple example that we're going to use here, is that a chemical messenger is going to cause them to open in order to drive an action potential. And another really important thing is that neurons have so many of these ion channels. A given neuron can have thousands, if not more than thousands, of ion channels, and the way that ions rush through these is incredibly fast. And so this is where we get this incredible dynamic reactivity of a neuron. So if we were to go through the steps in your book, there's one really important one that's kind of missing from the way that the book describes the action potential. And actually, your book does a very good job, but like with everything, there's some nuance here, and this is why I take you through this in a way that should be step by step by step. Most important piece of nuance that your book is missing is the 0th step, right? We need some drive from another neuron to open these ion channels that we were just talking about. And that means that we have to have some sort of a neurotransmitter come bind to one of these receptors in order to open the channel. And this is what happens in order for us to initially reach this threshold of excitation. So that's the first step. We have a threshold of excitation that's met because we've had some chemical signal come in. So we might have a lot of failed attempts, but when we have a sufficient number of inputs come in, that means that there's enough neurotransmitter released or enough neurons that release neurotransmitter to open up enough ion channels and depolarize this neuron we're looking at here enough to hit the threshold of excitation. So what happens when we hit this threshold of excitation is that we open up a special class of sodium ions that are called voltage-gated sodium channels. So one of the things that I think is really important is to break some of these terms down. So voltage-gated, right? And that means that these ion channels, as we said, every ion channel has something that causes it to open. And in the case of these voltage-gated sodium channels, they are gated by the voltage of the cell, which means that as the membrane potential becomes more positive, these sodium channels will open. And what this does is it causes this domino effect of sodium to rush into the cell. And because sodium is a positively charged ion, that means that the membrane potential becomes more and more and more positive. Okay? So then we hit step 2 here. What happens at this step 2? Well, it turns out that somewhere along the way, we also have potassium channels that are voltage gated. And these channels begin to open, and allow potassium to leave the cell. And what you can see here is that this rapid slope that we've had starts to slow down just a little bit, especially as we reach the top here. And that's because of two things happening. So of course we have potassium leaving the cell, which means that even though we have sodium rushing in and making the membrane potential more positive, potassium is starting to leave, which is working against that process, right? So this is what slows the acceleration down a little bit. And then at some point, these voltage-gated sodium channels hit their limit and they close. And when they do this, we call this becoming refractory. And this is what creates the peak in the action potential, this very important change in direction. These sodium channels, when they become refractory, they are unable to open anymore. So they become inactive for a period of time. And because they're proteins, all of these things have some bit of a dynamic to them, right? Which means in the case of these voltage-gated sodium channels, the protein actually has to move and kind of reconform to open and reconform to close. You could think of this as needing to open and close a door in your house or something like that, that there's a bit of a process where once you've slammed something shut, you have to kind of work against that momentum in the opposite direction, and you can't instantly reopen a door. It takes you a couple of milliseconds to be able to reopen. So we call this point where they become inactive their refractory period, and this happens for on the order of a few milliseconds. But at this point, we still have all of these voltage-gated potassium channels that are open, which means that potassium keeps leaving the cell and leaving the cell and leaving the cell. And so all of these positive ions are flowing out and out and out and out. And so this means the cell starts to return back to normal. So at some point, these voltage-gated potassium channels will close, but they don't all close at once. And so what happens is that in almost every case, and depending on the neuron and exactly what the potassium channels are and where they are, the neuron will overshoot a little bit. So the potassium channels start to close once we get below their kind of lower voltage limit. And then we have this overshooting that we call an after hyperpolarization. So, and this is a good thing. This helps to keep the timing of neurons. Right? This helps to make certain that even if another input comes in, that the neuron doesn't try and fire another action potential too quickly. And actually, this is one of the things that changes maybe how quickly a neuron can fire. Does it have a really big after hyperpolarization or a small one? These things all matter in terms of just what a neuron is able to do. And eventually, we have the sodium-potassium pump and all these other things happening. The cell gets back to its resting membrane potential, ready to receive another input and fire another action potential. And all of these things happen on the order of fractions of a second. Some neurons can fire 1 time per second. Some of them can fire even faster than that. Some as many as maybe 40 times a second when they're really active. And a lot of this depends on differences in the classes of these channels. There's not just one voltage-gated sodium channel or one voltage-gated potassium channel. There are many different classes of these. A diagram that I think is really helpful is this breakdown here. So what this really does is it just tells you what's happening in terms of time, and it allows you to break down the contributions of these two really important ions of sodium and potassium, and we have in what they're doing. So you can see that sodium channels open early and they kind of combine with this rising phase for the potassium channels in order to create the peak of the action potential. But remember, the potassium channels are allowing potassium to leave the cell. So what happens as they stay open and the sodium channels close is that we start to have kind of an opposing reaction here. So this is just a nice illustration that I think helps you to see kind of the dynamics and how the action potential takes shape. Now, what I'll say along with this is what you might gather from this diagram here, as you all try and get to know me and you start to think, what are the types of things that Dr. Barker might ask for a quiz question or something like that? And it would be really a good thing to know exactly what the different components of the action potential are, right? So, of course, there's this fundamental understanding of how all of the different pieces of the neuron come together to allow an action potential to happen. And then there's also what's happening at every step, what creates an after hyperpolarization. And you should think with a diagram like this, oh, that's right, the after hyperpolarization happens because potassium channels stay open and they continue to allow positive ions out of the cell, which means that the cell starts to get more negative for a few milliseconds. So one of the last important ideas that I need to leave you with is kind of a rule about the way that the action potential works. Now you could imagine, based on what we've talked about, that neurons are capable of doing a lot of different things. And in fact, there's really two ways you can look at this. On the one hand, neurons sort of have a volume knob to them, right? There are things that can change about a neuron for what it takes to hit the threshold of excitation. We can have inputs that make the neuron more hyperpolarized, competing with the ones that make it more depolarized or something like that. So in a way, this becomes kind of the volume knob where the neuron is deciding about processing and we can have it fluctuating between more positive and more negative. But when it comes to the action potential and sending a signal down to whatever the other part of the brain is, and as we've talked about, this happens at many times at great distance, the neuron only acts in really one way, and that's that it either sends an action potential or it doesn't. It becomes this binary decision. And so this is the idea of the all-in-one law, that an action potential is either sent or not sent. And that's what really causes that neuron to release its own neurotransmitter. That's the end goal that happens. And so this becomes a very important concept. And what this also means, and something that's sort of implied in this, is that it's not the size of the action potential that matters, because the size of an action potential never changes from the point when it's generated all the way out to the end of the neuron. And the reason this is important is because you could imagine some other parallel universe where the way that the brain works is to send bigger signals for a bigger message and smaller signals for a smaller message. And that's simply not what happens in a neuron. The all-in-one law, to repeat it and be very specific, states that if an action potential is triggered, then once it's triggered, it propagates without any change in size throughout the entire axon. Then the other alternative is that it's not triggered. So this is the way that neurons signal. So then how do we determine something like the strength of a stimulus? If we were to talk about loud sound versus a very soft sound, how does our brain compute those kind of things? Well, what happens in this case is that we use the rate of firing for the neuron. So the strength of a stimulus, and we're going to go into sensory systems in not too long here, it's going to be with us before you know it, is represented by the rate of firing, the number of action potentials per unit of time. So do I have 5 action potentials in a second, or do I have 20 action potentials in a second? This is what determines the strength in nearly every system that we're aware of, is the number of action potentials fired per unit time, or the rate of firing. And for all of these, the size of each action potential is always constant. So you can take this and apply it to any example that you want. Loudness of a sound, brightness of a light, but the most important thing is rate. Now, I want to point out one thing here on the slide, though, is that I say rate or timing. And this is because we do know of a few systems, and in the auditory system, there can be cases of this where sometimes the precision of timing can be equally important in influencing the next neuron down the line, or in creating a very specific memory. And we'll talk about a few examples of this when we talk about the idea of coincidence detectors for the auditory system. So there are some times where timing is very powerful, but for the most part, and the thing you should focus on for at least this upcoming quiz and lecture, is that rate is king. So how do we keep an action potential from decaying over distance? Well, this is where the idea of these myelin sheaths that we talked about last class and the nodes of Ranvier come in. And something that I think I hinted at last class, but I'll make explicitly clear here, is that the nodes of Ranvier and the myelin sheath are both equally important in doing this. Because the truth is that if we had an action potential that was propagating down an axon, and we didn't have a myelin sheath, that the signal would decay over distance, right? This is something we call the cable properties of a neuron. Signals do decay, electrical signals do decay over some distance. This is why you can't have a USB cable that's infinitely long without having something to amplify the signal, or why you need to get closer to a Wi-Fi router in order to have these signals passing back and forth. We all know we've seen these signals decay over distance. So the job of the myelin sheath is to insulate the signal and allow it to travel for longer than it would normally. But in truth, there is a slight bit of decay that happens as we're going under the myelin sheath. But then we get to the node of Ranvier, and something magical happens, and that is that there are voltage-gated sodium channels at every node of Ranvier. So what they do is that they allow kind of a miniature action potential, I guess is one way you could think about it, or a regeneration of the action potential by adding more sodium ions behind it. They're pushing it further and further down the axon in order to allow it to go. So if there are any baseball fans in the class, number one, I apologize for your shortened season. But you might think of this as the way, if you've ever seen a baseball game, that you get a baseball in quickly from the outfield. You keep throwing to the next relay in line. So this passing of the signal and allowing it to pick up speed by handing it to the next person who can throw it quickly, or if you want to think of a fast way to swim or run a relay race, it's the same thing. You put more energy behind the next person in line by kind of refreshing the signal as you go. So this is an incredibly important concept, this single idea of saltatory conduction, where we're able to have this signal regenerate in order to allow it to travel incredibly long distances. And in fact, we do have some examples of what happens when we lose the myelin sheath. This is what happens in some neurodegenerative disorders. Many of them are happening in the peripheral nervous system, but the result is the same, where signals are not able to get to the places that they need to get to. And so we have missed signals about some sensory input that's coming in, or we have problems with motor signals that are going out. So here's the point where I always try and do something a little bit informative, and I give you all an idea for just one lecture of the kind of things that I would be asking. This is our first kind of more complicated lecture. Told you last class you should think about the organelles that we talked about and their different definitions. But here's some important things to think about and that you should be able to answer following this lecture. How does neuronal excitation cause something like a withdrawal reflex, right? What's a very simple way that we pass signals between neurons to complete an action? And how can an inhibitory signal come and change this? There are also going to be things that are definition questions that you might have to answer on your quizzes. Something like, what is a resting potential? What does it mean for a neuron to be hyperpolarized or depolarized? And of course, there are going to be some things that I think of as application questions. You should be able to put some pieces together. Like, does all depolarization cause an action potential? Why or why not? Now, of course, things like this can still be put into multiple choice questions. So you should recognize that these are the sort of questions that you should be able to think about and answer, because maybe there would be a point where you're asked to think about whether something would or would not cause an action potential. We talked a lot today about diffusion and electrostatic force. So, of course, you'll have notes, and I pointed one diagram to you. You should be able to think about how these forces differentially affect chloride, potassium, sodium ions, at the very least. And a very good question to think about is, what's a case where these two are working against each other or with each other? This makes it very this is very important in certain cases for exactly how the action potential fires. And that's kind of a very high level mastery question that might be something worth thinking about, is why would I be asking a question like this of when diffusion and electrostatic force are working against each other or together? So thinking through that action potential diagram and all the steps, all different, I think 6 steps that we talked about. Back to other simple questions. These are in no particular order, but what's the role of the sodium-potassium pump? And then, of course, I think as I just hinted at, what are the steps involved in the triggering, the generation, and the propagation of the action potential? So these are a lot of different pieces, but we talked about what it takes to trigger an action potential, what it takes to generate it, and also something like, how does an action potential signal to the next neuron? Things like the rate code, the all-in-one rule. So what I'll leave you with today are a couple of videos. I think I had one up in an earlier slide. You'll probably want to go to the PowerPoint to get to these links that describe the action potential. I'm not going to claim that your book will ever do the best job, nor that I will do the best job of explaining something in a way that matches your learning style. So sometimes the animations and other cool things that these videos have that I can't easily put into the lecture are a better match for your learning style, especially if you're particularly visual. I leave you some extra time in order to do the reading and to be able to access resources like this. And with that, I wish you all the best. I hope you have a great rest of the week, and the other lectures should be up in a couple of days, if not at the same time as this one. I will catch you next time.